Minimum spanning tree. A minimum spanning tree or an MST is a spanning tree which is having the minimum weight among all possible spanning trees. So this is also a spanning tree, but the condition is this is the one which is having minimum weight among all possible spanning trees. So whatever properties we learned about spanning trees in the last lecture, all those properties hold for minimum spanning trees. Plus, there are some additional properties that will hold only for minimum spanning trees. So that is what we are going to learn in this lecture. First of all, what is meant by this minimum weight? How do you decide which is having minimum weight? First thing is, when we learned about spanning trees in the last lecture, we simply looked at the graph and we simply considered each of the edges of the graph. For example, if this is the graph, we simply considered there are some vertices A, B, C, D and E, and there are certain edges. But considering minimum spanning trees, you have to be concerned about the weight of edges. Each of the edge in a graph will be having some particular weight assigned. Based on this, you will decide minimum spanning tree. For example, if I am having weights 1, 2, 2, 4, 3. If these are the weights of edges, what will happen if I remove this edge from the graph? This is a spanning tree, but the question is what is the total weight of this spanning tree? So let me call this as spanning tree 1. For this, the total weight is 1 plus 2 plus 2 plus 3. What is this? This is 8. So 8 is the total edge weight for this particular spanning tree. So instead of removing this edge, what if I remove some other edge? Let us say I removed this edge. What is the weight now? If I remove this edge, for this the weight is 1 plus 2 plus 4 plus 3. I am just adding the weights of those edges which are involved in the spanning tree. Okay. So what is the weight here? This is a total of 10, which means my first spanning tree had a smaller weight when compared to the second spanning tree. So if you compare all the possible spanning trees from this graph, you will understand whatever we found in the first spanning tree, that is the one which is having minimum possible weight. So whenever you find a spanning tree which is having minimum possible weight among all the possible spanning trees of the graph, that is called as minimum spanning tree. About spanning trees, we learned many properties in the last lecture. For example, we learned that there should be v-1 edges in each of the spanning trees. We learned that there should be no cycles possible in spanning trees. We also learned that if you add an edge to a spanning tree, it will form a cycle and that cycle will be a unique cycle. So all these sort of properties or whatever we learned in the last lecture which are common to all spanning trees, they all apply to MST as well. In this lecture, we will be focusing on what is peculiar about MST, what makes minimum spanning tree special and what are the properties that are specific to minimum spanning trees. This is what we will focus in this lecture. So one thing, in the last lecture when we learned about spanning trees, we talked about one particular condition under which the spanning tree will be unique. We discussed there may be any number of spanning trees. It may be 1, 2, 3 or whatever. Any number of spanning trees may be possible for a graph depending on the structure of the graph. Then we also talked about a particular condition under which the spanning tree will be unique. What was the condition? The condition was that if your graph itself is a tree, then your spanning tree is unique because if you remove any edge from this tree, then that tree will be disconnected, which means you cannot remove anything from this tree. That means the tree you are having, that itself is the spanning tree. But in case of minimum spanning trees, let us see when will it be unique. Surely when it is a tree, it is unique. Other than that, what is it that gets added when it is a minimum spanning tree? So the condition is like this. If it is such that all the edge weights that you have are different, then in that case, your minimum spanning tree, that is MST, will be unique. That is what we learned just previously in the diagram what we had seen when we drew this graph. When we had this graph and we had different edge weights. Let us say we have 1, 2, 3, 4, 5. These are edges having different weights. Whenever you are having unique edge weights, distinct edge weights, then your MST will be unique. Why is it? Because there will be some particular edges which will always give you the least weighted spanning tree. For example, here if you remove the edge with weight 5, this is the minimum spanning tree possible for this graph, because if you remove any other edge, let us say this edge, and you keep 5, that will be having a higher weight because 5 is a edge which is having a higher weight compared to all other edges. So whenever you are having distinct weight for your edges, your spanning tree will be, your minimum spanning tree will be unique. So the next question is it the case that whenever you have some edges which are having equal weights, will you always have multiple spanning trees, multiple minimum spanning trees? So this is also not the case. The only point is, if you are having other edges which are having equal weights, in that case, it may be possible that there are multiple minimum spanning trees. Because let us say in this particular graph, if you change this 4 to 2, here you are having two different edges which are having weight 2. But still, minimum spanning tree of this graph is unique. Even if you change this also to 2, still the minimum spanning tree of this graph is unique. So in these sort of cases, even though there are multiple edges with the same weight, minimum spanning tree is unique. But there will be cases where when you are having, let us say, some multiple edges which are having same weight, you may end up in different possible spanning trees. For example, if you have a graph something like this, let us say this is my graph, and edge weights are 1, 1, 1, 1, 2. If these are the edge weights, then if I remove this particular edge, this is a minimum spanning tree. Similarly, if I remove, instead of this, if I remove this edge, this is still the minimum spanning tree for this graph. Instead of this, if I remove this edge, then also it is a minimum spanning tree. So in these sort of cases, you will have multiple minimum spanning trees when there are different edges which are having the same weight. Okay. So when you have multiple edges with the same weight, it is not necessary that there will be multiple minimum spanning trees, but there is a possibility that there may be multiple minimum spanning trees. So this is about uniqueness of minimum spanning trees. Another interesting property is, whenever you have a cut in the graph, that is, a graph is cut into, let us say, two disjoint sets. If these are the vertices in your graph, if this is how your graph looks, and these are the edges, and this is how, let us say, your graph is presently placed. If this is your graph, this side, I'll call them A, B, C, D, E, F. These are the vertices. Here you can see this part is one disjoint set and this part is one disjoint set if I remove these three edges. But the point is, whenever you have a situation when a graph can be cut into two disjoint sets, in such a condition, the minimum weight edge which is going across the cut must be a part of the minimum spanning tree. This is a condition. That is, if let us say you are having three edges here, AE is having a weight 2, let us say CD is having a weight 3 and BE is having a weight 5. In this case, the minimum weight edge that is crossing the cut is AE. What is it? AE is having a weight of 2 and it is an edge which is crossing the cut from one side to the other. Similarly, there are other edges which are crossing the cut. One is BE, which is of weight 5, and CD, which is of weight 3. Whenever you have a condition like this where you can put graph into two disjoint sets and there is a cut and there are few edges which are crossing the cut, then whichever is the minimum weight edge that is crossing the cut, that particular edge must be there in the minimum spanning tree. Does this mean the other edges in the cut will not be there in the minimum spanning tree? You can't say like that. The remaining edges, that is C, D or BE, these may or may not be part of the minimum spanning tree. You can't finalize this. This depends on the complete structure of the graph. But whenever you have a cut, you can always say that whichever is the minimum weighted edge that is crossing the cut, that should be there in the minimum spanning tree. Okay. And one more thing is, whenever a cycle exists in a graph, one thing you can say about minimum spanning tree is the heaviest edge that is part of that cycle, that can be safely removed without disconnecting the graph. So whenever you have a cycle in the graph, let us say this is your graph A, B, C, D. If this is your graph and you have a cycle and these are having edge weights 1, 2, 3, 4, then whichever is the heaviest edge, here it is 4, that can be safely removed whenever you are constructing the minimum spanning tree. See, here it is very evident because I just took a very simple graph which is having only one cycle. But if it is a very complex graph, let us say you have a very complex graph with a lot of vertices and all. But even in this sort of a case, if there is a cycle, for example, here you can see a cycle. From this cycle, whichever is the edge which is having maximum weight, the heaviest edge, that can be safely removed. Still, it will become a minimum spanning tree. You may have to deal with other edges, but as far as this particular cycle is concerned, you can safely remove the heaviest edge of the cycle. Okay. And generally, in any MST, when you take any MST, whichever is the heaviest edge, that edge represents the weakest link of the MST. What is a weakest link? Weakest link means, let us talk about any real world application. Whenever you have a real world application, this weakest link is what you generally have the highest cost on. So you would say this is the highest cost link or maybe slowest bandwidth link. That is, if you are connecting something, you are using some network or something, then whichever is having the slowest bandwidth or maybe highest cost to construct, this is what you generally have as the weakest link. That will be the heaviest edge of an MST. So whenever you have an MST, the heaviest edge is always your weakest link. And where is this MST used? It has a lot of applications in networks and all. And it is even used for approximating some hard problems like TSP or something. If you want to approximate, you use MST. So this is it about MST. For spanning tree details, please go to the previous lecture. In detail, we discussed about all the properties of spanning tree. This lecture was specifically for minimum spanning trees. Okay.